Hello, my name is Jim Mullins, Senior Principal Scientist at Simulations Plus, and today I'm going to talk to you about IVIVC and GPX. What is an IVIVC? It's a mathematical function that correlates an in vitro dissolution profile with an in vivo response, like plasma concentration time profile. In GastroPlus, you can use the mechanistic methods which deconvolute the in vivo dissolution versus time. You can use a traditional method like Lou-Riggleman, which deconvolutes the in vivo bioavailability versus time, or you can use a model-independent method like numerical deconvolution. Correlation functions in GastroPlus available are the linear, polynomial, power law, and time shifting and scaling methods. Once developed, an IVIVC function can be utilized to predict the plasma concentration time profile for a different formulation variant with different in vitro dissolution profile. Today, we're going to be talking about this sodium valproate example. On the right-hand side, we have in vitro data for 5 formulation variants: slow, slightly slow, medium, slightly fast, and fast. And we have plasma concentration time profiles for each of those formulation variants on the left-hand side. That is a requirement for building an IVIVC. Obviously, you need in vitro dissolution data and the in vivo plasma concentration data. So with that, let's open up GPX and get started. Alrighty, so we have GastroPlus open here. So let's open a project. Let me click Browse. And my project is under my training video folder, IVIVC valproate. So we'll open that up. And you can see the project is loaded. So let's take a quick look at the in vitro data for these records here. So we pre-created all the records for those 5 formulations. So let's go to the observed data first. Again, you need both plasma concentration and in vitro data for each formulation. So let's look at the exposure data first, which contains the plasma concentration data. Let's select the slow tablet here, and you can scroll down and you can see that we've already input in the time concentration profile for the slow formulation. In terms of the in vitro dissolution, you can select data type, select in vitro dissolution release, and then again select the slow tablet for the group name. And you can scroll down and you can see that we have the fraction released over time. And if I click the distributions panel here, you can see that we have Weibull parameters that have already been created for the in vitro release. And that's the red curve here based on these timescale and shape parameters. So we've done that for every single formulation. We don't have time to do that manually, so keep that in mind that we've already pre-created all of these records here. So let's go to the dosing formulations. So we've created CR tablets for each of these formulations: the fast, moderate, slightly fast, slightly slow, slow formulation. The route is oral. It's a controlled release integral tablet, and it's dosed to the stomach. If we click the controlled release panel here, you can see that we've set up the Weibull distribution parameters for the in vitro dissolution release group from the fast tablet for the fast formulation. So again, you need to match up the in vitro dissolution profile with the actual formulation you're working with through this controlled release input here. So we've created that for each one of these formulations here. In terms of the physiology, we have an average subject of 82 kilograms for these set of simulations. We've created records both with compartmental pharmacokinetics. So on the pharmacokinetics tab, you can see that we have 2 compartment pharmacokinetics here for sodium valproate. This was created using PK Plus within GPX. And then we also have a PBPK model for sodium valproate using the default Lukachova tissue partition coefficients for perfusion limited tissues. And then we also use FUP times GFR for the clearance here, because this compound is cleared specifically with renal clearance. And then if we go to simulations, you can see that we have set up a simulation both for the PBPK and compartmental pharmacokinetics. So you can see at the bottom of the simulations list here, we have a comp PK version of every simulation. And then also above, we have the PBPK version, which is just the simulations without comp PK added to the record name here. So let's just run one simulation to get an idea of what we're seeing here. So let's run the CR tablet 500 mg slow formulation. And we'll just click run here. And here you can see we're now going to have a prediction of the in vivo PK just with the in vitro dissolution determining the rate of input of drug dissolving in the intestinal lumen, and then thereafter the permeability through the intestine and arrival into systemic circulation produces that PK curve that you see. So let's build an IVIVC though for this data set. So to do that, you're going to go to the right-hand panel where the modules are located and select IVIVCPlus. Alrighty, so now let's set up an IVIVC for the compartmental pharmacokinetics for the Lou-Riggleman method here. So the first thing we need to do is create a subject for deconvolution. So let's expand the subject panel and let's add a subject. Of course, here we're doing an average deconvolution. We don't have the individual subject data. So we'll create an average subject, click OK. And then we need to set up the inputs for every formulation. So here we need to set up the slow, moderate, slightly fast, and fast formulation here. So let's click add, and we'll start with the slow formulation first. We'll click OK. We need to set up the dose schedule, the dissolution series, the base simulation, and exposure data or plasma concentration data for this record. So let's just go in here and set the dose schedule to the slow formulation, the dissolution series to the slow. The base simulation here, we're going to use the compartmental PK because we are going to do a deconvolution with Lou-Riggleman method. So I'm going to use the slow CR tablet comp PK. And then exposure group, I'm going to use the slow plasma concentration data. And that's all you need to do to set up one of the inputs. Now I'm going to repeat that process for the other formulations, and we'll get back to you in a second. All right, so now we've set up all the different formulations from slow to fast. So now we can perform the deconvolution. So let's minimize the input panel here by clicking the inputs panel button. Click the deconvolution button, and then we'll select the fast, moderate, and slow formulations. Again, we have just an average subject, so we'll select the average subject. And then we want to make sure that Lou-Riggleman two-compartment method is selected since we have a two-compartment PK model here. So let's go down to the deconvolution run and results panel. We'll expand that and we'll click deconvolute. GPX will pretty quickly deconvolute the in vivo bioavailability versus time, and it'll plot that in the upper left-hand plot here. On the upper right-hand plot, we'll have the plasma concentrations versus time. And here you can see it's a perfect fit of the data because it's doing a deconvolution. So obviously we're fitting the data at this point. So nice fit to the data. On the lower right, we have the Levy plot, and on the lower left, we have the AUC versus time. If you want to get a little bit better view of these plots, you can expand them by clicking the pop out button here. And then this will pop out the results, and then you can maximize them and get a little bit better view of what you're looking at there. And then when you're done, you can click the X to close that down. Okay, we've completed the deconvolution. Let's minimize the deconvolution panel and let's go to the correlation panel. So now we're going to create a correlation between the in vitro dissolution and the in vivo fraction bioavailable. So we're going to select linear, power law, second order, and third order polynomial. And then we're going to go down to the correlation run and results and expand that. And we're going to use the default AIC criteria for selecting which model works the best here. And we're going to click Form Correlation. Here you can see the second order model provides the best AIC, which is the lowest in this case. And if we scroll down, you can see a plot of the in vitro release on the x-axis versus the fraction bioavailability on the y-axis. And then again, all the different formulations data is plotted there. It also plots all the different individual correlations that have been shown there. So you can select and deselect whatever you want. You know, if you want to deselect the third order, linear, and power law, you can, just to show the best fitting second order polynomial there. Okay, so that's really it for the deconvolution step. We have an IVIVC now. We can save it. So I'm going to save this as the compartmental deconvolution, and we're going to save that correlation. So that's available now within GPX to use when running simulations in the program. If we go to the convolution tab, we can do internal and external validation. So I'm going to minimize the correlation and run in results and maximize the convolution panel. And we'll select the fast, moderate, and slow formulations. We'll select the average subject, and we'll click convolute. And so now what we're doing is essentially using the IVIVC we've just built and rerunning the data that was used to build the IVIVC through the correlation to do the internal validation or prediction of the error. So here you can see that the AUC prediction error is all pretty good, less than about, the maximum value is about minus 5.7%. This would pass FDA criteria for the point estimate being below 15%. And the Cmax prediction error ranges from minus 3.2 to 15.84 for the moderate formulation. So this would fail the point estimate just barely for the moderate formulation. And then the average Cmax and AUC mean error are 8 and 4%. And these would pass the 10% criteria value set by the FDA. You can pretty quickly validate your IVIVC using GastroPlus's built-in tools. Of course, you can do external validation as well. So if we deselect the fast and moderate, we can run the slightly fast and slightly slow and click convolute, and it'll do the external validation, running the IVIVC on data sets that were not used to build the IVIVC. And here you can see the point estimate for AUC is 6.6 and 14.1% for the fast and slightly slow. So this would fail FDA criteria in this case. I think all the point estimates have to be below 10% in this case, and the mean has to be below 10%. So again, the mean Cmax and AUC is 20% and 10% error. So this would fail the FDA criteria in this case. So let's now do a mechanistic IVIVC. So let's collapse this convolution tab here, and we'll collapse the correlation tab and go back up to the inputs. And now we need to basically link the PBPK version of the model to these records. So what I'm going to do is go through each of these inputs and select the base simulation as the PBPK version. So I'm going to go to the slow input first, and then select the CR tablet 500 meg slow. And I'm going to go to the slightly slow, and then select the PBPK version of the model, which is the slightly slow version, moderate. Instead of the compartmental PK, again, we want to select the moderate formulation. Slightly fast, again, we will select the slightly fast without the comp PK label. And then fast, we will select the CR tablet 500 meg fast base simulation. So now we are going to switch to the PBPK version of the model and do a PBPK mechanistic IVIVC. So everything's set up. We can go to the deconvolution tab. We already have our input set up correctly and our subject selected, but we need to change the deconvolution method to mechanistic. In this case, we need to set the Weibull settings for the mechanistic deconvolution because we're going to be deconvoluting the in vivo dissolution. And we need to select the different Weibull parameters that we want to utilize here in the optimization. So we're going to select initialize estimates, which uses an automatically generated initial estimate for the optimizer. And we want two phase Weibull functions for this optimization. So I'm going to select each one of these fast, moderate, and slow formulations and set it to two-phase Weibull deconvolution. So now we have a two-phase Weibull function set up for the deconvolution. We're going to go to optimization settings and make sure that we have the venous return selected for the objective function. And then we're going to deconvolute. Here you can see the previous result, the compartmental model is still visible. We're going to now do the mechanistic deconvolution by just clicking the deconvolute button. And now it's going to optimize the in vivo dissolution rate for each of these formulations that best matches the plasma concentration. This is going to take a long period of time, so we'll just wait until the optimization starts here for this first record, which is the fast record here. It looks like now we see the R-squared value and the current Weibull parameters that it's optimizing along with the step size and the objective function value. So we're currently on iteration 2. We'll check back when all 3 of these fast, moderate, and slow records have been optimized in terms of the in vivo dissolution. All right, so the deconvolution is completed for the mechanistic deconvolution. We now have a plasma concentration profile for each of the formulations. We have the deconvoluted in vivo release plotted up here on the upper left-hand side. And again, we have the Levy plot and the AUC versus time on the lower right and lower left-hand plot, respectively. We can now build a correlation for the mechanistic deconvolution by going to the correlation panel. And again, it's saved our settings from the last correlation, linear, power law, second order, and third order. We'll keep those selections, and then we'll run a correlation by clicking the correlation run in results panel. Click form correlation. Again, we're using the AIC for the criteria. And again, it's going to find that the second order correlation is best for this data set. I'm going to minimize the correlation panel and open up the convolution panel. Here we can unselect the slightly fast and slightly slow and select fast, moderate, and slow formulations. And we'll do the convolution using the mechanistic deconvolution. Alrighty, so let's scroll down. And here you can see the point estimate for AUC and Cmax are all below the 15% limit for the FDA criteria. I think the highest error for the AUC is about 6.6%. The highest for the Cmax is about 11.5%. And the average Cmax and AUC error is 7.7 and 3.8%. So this would pass the 15% point estimate error and 10% average Cmax and AUC error for FDA validation. Of course, we can do an external validation as well. Let's select the slightly fast and slightly slow formulation. And we'll do the convolution. And in this case, we passed the Cmax error, 6.8 and 10%. And one of the formulations passes the AUC point estimate of 8.2, but one's a little bit high at 3.26. And the average AUC is just out of range. So perhaps if we ran the deconvolution a little bit longer, the optimization, maybe we would get slightly better results, or maybe if we used a different objective function, we could just get over the goal line here and pass the FDA criteria. However, this shows much better results than the compartmental deconvolution for sure. We can save this IVIVC. Let's go back to the correlation run and results, and this time we'll call this the mechanistic deconvolution, IVIVC, and we'll save that correlation. In the messages, you'll see that it is just telling you that you've saved that to the database here, and it can be used in the future. So let me really quickly show you how you'd use this IVIVC for a different formulation. So within our dosing, if we go over to the dosing tab here and look at formulations, you can see that we have a test formulation here. So let's use the IVIVC that we've developed to run a simulation for the test formulation. So to apply the IVIVC to this test formulation, all you need to do is go to the controlled release panel here. And instead of using the in vitro dissolution data here, what we're going to do is use the IVIVC that we've generated to convert the in vitro dissolution for the test formulation into the in vivo dissolution. To do that, you need to change the profile from the Weibull parameters to the tabulated, and then select the Use IVIVC Correlation button here. And then we'll use the mechanistic deconvolution that we'd created. Use this polynomial here to convert the in vitro dissolution for the test formulation into an in vivo dissolution profile. So let's click this Create In Vivo Series. And you can see in the message center, we now have a new in vivo controlled release profile that has been created from the IVIVC. So now we could select that here and run a simulation with that. However, you might want to generate Weibull parameters for the in vivo dissolution. So to do that, you can go to the Observe Data. And now we can select the in vivo controlled release data, and we should have a value for the test formulation now, which we do. So this is what was converted from the IVIVC. Of course, we only have the in vitro dissolution profile data points, we haven't fit a Weibull yet, so the red curve is not matching the in vitro data. We can very easily do that by going to the distributions panel and then scroll over. And I'm going to select the data here and click initial estimates. And then I'm going to use a two-phase Weibull function here. And I'm going to make the initial guess 0.5 for phase 1. And then let's just click fit and see what we get here. That looks pretty good. So now we have Weibull parameters as well that fits the in vivo dissolution data that we've generated using the IVIVC. So I'm going to save this and go back to the dosing. And for the test formulation here, I'm going to now set the in vivo controlled release group. And I'm going to use the distribution or the Weibull parameters that were generated. Now I can go to the simulation tab, go to the test formulation, and then run a simulation based on that in vivo dissolution data that we've generated from the IVIVC. So let's click run. And that's how we would predict a new formulation based on an IVIVC that we've developed on an existing data set. So thank you very much. Again, my name is Jim. You can find our website for more information. Again, we have more tutorials available for GPX, and one that will tie in nicely with this would be the virtual bioequivalence. You can use IVIVCs to do virtual BE in GPX, so I urge you to check that out. Thank you and have a good day. Bye.